Okay, good morning, everyone. How is everyone doing today? Good? We have some seats open here if you guys want to come up front here. My voice okay in the back? You guys hearing okay? Okay, cool. Well, good morning and welcome to this session. This session is about Catalyst 9000. In Cisco, we love the number 9, right? So we have all kinds of 9,000 products. We have Catalyst, we have Nexus, we have ASR, some of the major ones, and there are more. Just want to make it very clear that this session is about Catalyst 9000. So we are going to talk about everything Catalyst. We will not cover anything on the Nexus side or the ASR 9000 side, okay? All right. Enterprise networks have drastically changed in the last 15, 20 years. When I started my career early in the 2000s, I was working at a multinational company which had a pretty decent network as a network engineer. And the networks that we had at that time, it was based on your favorite Catalyst 6K, right? I see some nods there. People love it. You guys love it. I know that. And every port that was going into that Catalyst 6K was one type of end device. You guys can guess that, right? It was a desktop PC. Every port that is going to that Cat 6K was a desktop PC. Fast forward today, you just go to your wiring closet and look at the types of ports. You will see a lot more varieties depending on what kind of organization you are. When I look at my customer networks, a lot of times, I see ports getting connected to the access points, video cameras, IP phones, of course, desktop PCs as well. But more interestingly, vending machines are getting connected to the networks. Blinds in hotels are getting connected to the network. LED lights are getting connected to the networks. A lot of new IoT devices and sensors are getting connected to the network. That's how the enterprise network has changed over the last 20 years. And as you see the variety of devices coming in our networks, the complexity of networks has gone really up. And now you have to deal with that same network in a different way. And when you look at the challenges, because of all of these different devices that are getting connected and the applications that are running on top of that, we see challenges in 4 key areas. Number 1 is security. Security is top of mind for everyone. I'm pretty sure for all of you guys as well. IoT devices are just exploding, right? There are all kinds of stats. I don't have to mention that here. But they are going to be in billions going forward and trillions in a few years. Mobility is an essential thing. It's not a luxury anymore, right? And then we have cloud-based applications. I used to be a very heavy user of Excel, Microsoft Excel. Most of my sheets now are in a Smart Sheet. Most of my folders are going to the Box folder. I'm pretty sure a lot of you are using the same things. And that has made the challenges that we typically have or used to have in the enterprise network different today. And that was the reason to introduce the Catalyst 9K about a year and a half back. Those were the challenges that we thought about how we can address these challenges for our customers by bringing a platform that can handle these challenges. And that's the story behind the Catalyst 9K. So this session is going to talk about everything about Catalyst 9K so that you have a good understanding of the Catalyst 9K products in depth, and you are able to make better decisions when you are deploying or when you are making a purchase decision. Right? That's the goal of this session. A little bit about myself. My name is Muhammad Imam. I lead the technical marketing team for enterprise networks at Cisco. I've been at Cisco for about almost 11 years and have been working in different roles. I started with engineering, so I used to be in software engineering before I moved to technical marketing, and have been working on multiple products, starting with ASR 1K, Catalyst switches. I was one of the initial TMEs. TME means technical marketing engineer, working on the Catalyst 3850. And since then, I have been with Catalyst for most of my technical marketing engineering career. And recently, I have taken a lead role where I'm leading the enterprise networking team of routing, switching, and wireless. I do have a CCIE, and I do have a Twitter account. And I'm getting better on Twitter. I have about, I think, close to 200 people following me. So that's an improvement from last year. I think I had 150 last year. All right, so that's a little bit about myself. How many of you guys are attending Cisco Live for the very first time? OK, great, welcome. How many of you are CCIEs? OK, great. Well, you better keep me honest in this session. OK, so quick agenda for the 2-hour session that we have today. We are going to introduce the Catalyst 9K product line. We are also going to talk about the architectural view. And we are going to go a little bit more in depth and talk about the ASICs and the IOSXE software architecture. And then we are going to talk about high availability in Cat 9K, as well as the QoS, quality of service, as 2 topics in addition to the platforms. And we are going to be brief on that. Won't have too much time to go in depth. But we want to touch on some of the interesting things that we have in the Catalyst 9K, and we'll wrap it up. OK, with that, I would like to get started with the Catalyst 9000 family of products. We started Catalyst 9000 in June of 2017 with 3 primary products, Catalyst 9300, 9400, and 9500. But since then, we have been adding a lot of other components, as well as a lot of other new products in this Catalyst 9K family. So we have added Catalyst 9500 high performance, which we will talk about in the next few slides. We have added some of the new modules, new power supplies, new SKUs on the Catalyst 9300, 9404, a smaller chassis on the Catalyst 9400. We have added some new line cards as well, like 48 port of SFP and 24 port of SFP line card on the Catalyst 9400. Just last month, we have introduced a brand new product line, which is the Catalyst 9200. How many of you have heard about Catalyst 9200? OK, great. So we'll talk about this a little bit more than the others, because the others have been out for a while. I'm going to double-click on the Catalyst 9200 a little bit more in this session. And we have introduced one more Cat 9K. Any guesses? 9507. Say it again? 9507. 9800. Yes. We have introduced the Catalyst 9800. This is the first Catalyst wireless LAN controller that we have introduced last month. And this is running the same operating system that we are running on the rest of the Catalyst 9K family. Now, this is outside the scope of this session. It's a wireless LAN controller. This session is more about Catalyst switches. So we'll not talk about this particular Catalyst 9800 in detail. However, if you are more interested into this, there's a session. You can get into that session or maybe watch it online. So we are going to start with the building blocks of the Catalyst 9K. It's always important to know the building blocks of a product, because that's what defines it, and that gives you an in-depth view of what product line is able to accomplish with the building blocks. The Catalyst 9000 family of product, the switches, they are all based on common ASIC and common software. In addition to that, other than one, all of the members of the Catalyst 9K family are based on x86-based CPU, and we'll talk about that exception. When we started working on the Catalyst 9K, we wanted to bring consistency across the platforms in the enterprise network switches. Those of you who are familiar with the Catalyst 2K, Catalyst 3K, Catalyst 4K, and Catalyst 6K in the past, these products have evolved over time. And you guys have probably seen a lot of differences between the Catalyst 2K, 3K, 4K, 6K. And there's a lot of history behind them. But the end result to our customers was inconsistent behavior, inconsistent hardware, and inconsistent software. With the Catalyst 9K, we are bringing a lot of simplicity and consistency in the platforms that you need to deploy in the campus, in the enterprise networks. All of the Catalyst 9K run the same operating system, which is based on iOS XE, and they run on the same hardware, which is based on the ASIC that we have, which is called UADP ASIC, Unified Access Data Plane ASIC. This was first introduced with Catalyst 3850, and then it has really grown into a family of ASICs, and we will talk about that family. So these are the three building blocks that we have in the Catalyst 9K that you will see consistently across the Catalyst 9K family. Now let's talk about the ASIC first. The UADP ASIC that we have and the UADP ASIC family that we have in the Catalyst 9K, this is the most important hardware piece that we have in the hardware. This is the brain of the system. Everything gets processed through the ASIC. All of the processing are happening through the ASIC. Rest of the components that we have in the hardware are assisting the ASIC. But ASIC is the fundamental building block in any switch. Now, ASICs have been traditionally very fixed piece of hardware in the past. What we have done here with the UADP ASIC, we have broad programmability and flexibility in the ASIC. And we'll talk about that a little bit more once we get to the ASIC section. But what that really means is investment protection for our customers. That means when new technologies come out, the ASIC can adopt it. We don't have to change the hardware. We don't have to make a new ASIC to have the feature support, to have the new protocol support. We don't know. The technology is changing very fast. We don't know what's going to happen in the next 5 years, in the next 7 years. If there are new protocols that evolve, we would like to have our customers have a hardware that can adopt those technologies without changing the platform again, right? And that's the story behind the UADP ASIC. This is a unique feature in the UADP ASIC, which is the flexibility to adopt new protocols. We also have what we call it universal, what we call it adaptable tables. Adaptable tables mean the tables, which is part of the memory that we have inside the ASIC, they can be carved in different ways. So if you are deploying your Catalyst 9K in a traditional deployment today and want to go to software-defined networking tomorrow with software-defined access, for example, You might have to change certain tables with different requirements. In a traditional requirement, you might need more L2 routes, while as you go to the software-defined networking, you might need more L3 routes. If your tables are fixed, that's going to be hard. But the tables in the UADP ASIC is flexible as well, which means you can carve those tables in different ways. You can make the L2 table larger or smaller based on your deployment. And that flexibility is there in the ASIC. And as always happens with new ASICs, we have enhanced the performance and scalability compared to the previous generation of this ASIC in the UADP ASIC that we have in the Cat9K. Now, the UADP ASIC can go up to 1.6 terabits per second. That's a lot of bandwidth in one ASIC, right? And that's what makes most of our fixed platforms line rate on all ports. The second thing that the second building block that I would like to focus on is the x86-based CPU. Now, the x86-based CPU is an important component. CPU is always an important component because that's what deals with the control plane of the network, right, or control plane of the networking device. That's where your protocols decide which routes need to be generated, right? That's where BGP runs. That's where OSPF runs. So all those features, the control plane of those features are running in the CPU. But the control plane of the features can run in any CPU. Why do we need an x86-based CPU? Well, in today's world, the developers are evolving new applications every single day. And networking is no exception. We are seeing the same thing in the networking space as well. We have a lot more new applications in the networking space. To utilize those applications, we need an x86-based CPU. Why? Because most of those applications are built on an x86-based CPU. And as you probably know, once the application is built on a specific type of CPU, it can easily run on that type of CPU. But if you want to run on a different type of CPU, so for example, ARM-based CPU, that will require a different compilation of that code, of that application. So by having the x86-based CPU, we are giving our customer an opportunity to run different applications. For example, you can run applications in a container inside the Cat9K. So you can run Wireshark. You can run Perf Sonar. You can run Kibana, for example, and get some stats and other monitoring tools you can run as well. So x86-based CPU gives you a lot of power to run the different applications on the Catalyst 9K. The third key component on the Cat9K is the software. And that is the Open iOS XE that we have. Now, the iOS has evolved over the years in Cisco. Its history goes back all the way to when Cisco started in 1984. And through the years, it has really evolved into a very rich operating system, very feature-rich. And iOS XE is an operating system that has a new architecture. It's a really modern architecture that can handle some of the new things that we are seeing in the market. So for example, this operating system is capable of doing programmability and automation, hosting applications, having model-based APIs. These things are possible with this operating system because we have re-architected the iOS into iOS XE a few years back. And that also brings a lot of consistency in the Catalyst 9K family. And we'll talk about that a little bit more as we go forward. Now, x86-based CPU and operating system support is great. But as you start putting new applications on the Cat9K, you'll need storage. And typically in the networking device, what is the best storage we have seen so far? 8 gig, right? With the Catalyst 9K, you can take the storage on the Catalyst 9K up to 1 terabyte of storage on the Catalyst 9400, 120 gig on Catalyst 9500 and Catalyst 9300s. Okay, that gives you a lot of storage space to store applications, but you can use that space for other things. For example, you can use that space to store your images or log files, system logs, and so on, right? All right. Now, when we started building the Catalyst 9K, we also thought about what are some of the user experiences that our customer used to have with the previous Catalyst products. And we wanted to simplify things, and we wanted to make things better for our customers. So we came up with user-centric design on the entire Catalyst 9K family, and you will see that consistently across the product line. So I'll talk about some of the cool features that we have added in the Cat 9K. One of the features that we have added is the blue beacon. How many of you are familiar with the blue beacon? You know what's blue beacon? Okay, some of you are familiar with blue beacon. You probably have seen these blue lights in the data center products a lot of times, which can be enabled from the console, right? And if you have that capability of enabling that blue light from the console, that means you can identify that device very easily. So if you have to, for example, change a line card in a remote location or a stack member on a remote location, you can enable the blue beacon from the comfort of your office and send someone in the remote office, for example, ask someone to kind of pull it out, right? It's very easy to identify instead of mixing it up and later finding out, oh, I pulled the wrong line card, right? We have all seen that. OK, so that's cool. We have also added RFID tags on each of the Cat 9K. And in the modular chassis, we have added on every single component. How many of you attach an RFID tag on your networking devices? Anyone? No one? OK. Well, I have seen some customers, as soon as they receive the product, they attach an RFID tag so that they can track it. It's for tracking purposes. What we have on the Cat 9K is we have RFID embedded in the Cat 9K. So you don't have to attach an external RFID. It gives you some good information on that RFID tag. So you can have an RFID scanner and scan it and get this information, which has serial number, its PID, and some other information. In fact, you can customize that as well. And you can put some information that you want. For example, you can put that this switch is for building 5, floor 2, wiring closet 3. Right? You can do that. How many of you have Catalyst 4500s in your network? OK. So Catalyst 4500 has this fan tray on the left side, right? You guys familiar with that? I have seen customers passing some cables through the handle of the fan tray. Have you guys seen that? OK. We have all done that. And what happens when you have to service that fan tray? You have to take all the cables out. Right? It's not the best practice. But if you are in that situation, the Catalyst 9400 gives you an opportunity to take the same fan tray from the backside as well. So you don't have to always go from the front. It can be serviced from the front as well as from the back. So that's a cool feature, I think, because that gives you a little bit more flexibility. But we should all follow the best practices of cabling. Okay. We also have something called barometer in the Catalyst 9400 fans, which basically detects the altitude of the Catalyst 9400. And based on that, it adjusts the fan speed based on the temperature sensors and the height. These features makes the cooling better in the Catalyst 9400. OK, that's a cool car. How many of you have this in your garages? No one? Well, I have one, but it's not in my garage. It's a small one. Usually sit on my table. Why we are talking about this car? This car is designed by a company called Pininfarina. And Pininfarina has designed the exterior of the Catalyst 9K as well. OK, and what that means, When Pininfarina work on some of these designs, what they typically do is they define an industrial design language, IDL. And based on that IDL, they design the product lines. That brings consistency, and that brings some of these features that you are seeing in the Catalyst 9K. Okay? And it's a minor point, but that basically leads to consistency and simplicity across the platforms. The need for speed. The need for speed in the network, and that reminds me, the need for speed, the game I used to play a long time back. These days, it's all about Fortnite, right? You guys play Fortnite? Anyone? Well, it's very popular in US for some reason, and my son always sitting on the iPad and trying to get on Fortnite. But that was the old era. Now, if you look at the networks, and if you look at the bandwidths that we are getting from the newer applications, there are few new trends that we are seeing rapidly evolving. 11AX is coming out very fast. At the end of this year, I think it's going to be available. I mean, some companies are claiming its availability right now. AR, VR, augmented reality, virtual reality. You guys probably have seen some demo when you were going to the World of Solution. These things are getting more popular. And 4K video is a reality now, right? And we are talking about 8K video now. All of these different types of applications, they put a lot more pressure on the network from bandwidth perspective. And when you start looking at the different challenges that you have in the network from bandwidth perspective, one of the things that you will see that your access layer might be short on bandwidth. All these applications, they first connect to the access layer, to your Ethernet port, right, the copper port. If your copper port is 1 gig and your application can go more, you have a bottleneck right there. And that's the scenario that we are going to have with 11AX. That's a scenario that we could have with 11AC phase 2, right? The standard can give you more than a gig. Even if you have a little bit more than a gig on the wire, that means your bottleneck is right there. Now, if we look at our networks, we have a good amount, I think more than 70% of the copper Ethernet cables that we have are still Cat5e. And Cat5e cannot go to the next standard that was available earlier, which is 10 gig. So if you have a Cat5e, you cannot go to 10G base T, right? That's why Cisco started working on this standard with an N-base-T alliance and word on this standard that is called multi-gigabit standard, which brings some new speeds that can be used, that can be run on the same wire, the same Cat5e wire that you have. And those new speeds are 2.5 gig and 5 gig, okay? So these are the multi-gigabit speed. What that really does is, if you have Cat5e cable, that bottlenecks get removed with the multi-gigabit port, and now you can achieve up to 5 gig, 2.5 or 5 gig, right, depending on your wire quality and the distances. Okay? So with that, now you are able to run 11AX without a bottleneck, right, and other applications. The multi-gigabit port can also run 10G base T if you have good wires, which means if you have Cat6a wire, it is also 10G base T, right? But you have to look at the maximum speed that you have on the multi-gigabit port, okay? And we'll talk about some of that. So we have a full multi-gigabit portfolio on our access layer products. On the Catalyst 9300, we have multiple of them. On the Catalyst 9400, we have a line card. And we also have a Catalyst 9300 multi-gigabit module. This module has 4 ports of multi-gigabit, full multi-gigabit, but they don't have PoE. So you have to remember that. So you cannot run PoE out of that, but you get up to 10 gig of bandwidth from that port, okay? Now, as you go multi-gigabit in your access layer, what's going to happen to the next layers of your network? Those will get more bandwidth as well. So as you go from 1 gig to 2.5 and 5 gig here, you have more bandwidth here. And what's the solution? One of the solutions that you can have is you do a port channel and you go multiple links, right? You can do that. That will solve the problem, but at an expense of another port. You have to add another port there, right? What is another solution? Another solution could be you go to 40 gig, right? That's available as well. But when we look at so this has some of the challenges because you need an additional port. In some cases you might have, in some cases you might not have, and you need another wire as well. In this case, you need to have a 40 gig port going up. Okay? Now, if you look at the 40 gig, from 10 gig to 40 gig migration has some challenges. And we have seen some of those challenges when we were migrating from 1 gig to 10 gig in the last 5, 10 years. When we came up with these new connectors, the migration was pretty difficult because now you have a different form factor. When we went from SFP to SFP+, the migration was much more seamless. Similarly, when we are going from 10 gig to 40 gig, we are seeing those challenges. One of the better alternatives that we have is a 25 gig, because that does not change your form factor. You can run it on the same cable. And we have introduced an SFP+ and optics, which can run at 10 gig as well as 25 gig. With just a CLI command, you can change the speed from 10 gig to 25 gig, right? It's a dual rate optics. And with that optics, you will be able to run 10 gig today. In future, once you have the requirement of 25 gig, you can go 25 gig, okay? Now, you get multiple benefits out of this. Number one, you can go the same distances while going from 10 gig to 25 gig. Your oversubscription ratio still remains the same. As you go from 2.5 gig to 25 gig, the oversubscription ratio is same because earlier you had 1 gig and 10 gig, right? So the ratio stays the same. And the speed migration with the dual rate optics, that is a investment protection for you as well, okay? Now, what are the different products that we have on the 25 gig? We have multiple products in each of the Catalyst 9300, in each of the Catalyst 9000 family. So on the Catalyst 9500, we have two products, 24-port and 48-port 25 gig. They can also run on 10 gig and 1 gig. Then on the 9400, we have a new supervisor, which is XLY. Y stands for 25. It has two 25 gig uplink ports. On the Catalyst 9300, we have a uplink module, which has two 25 gig ports. And then we have the optics. So we have the full portfolio to utilize the 25 gig in your network. Okay. So when you go 25 gig in your access to distribution, what happens to the next layer of your network? That has more bandwidth, right? As you go with more bandwidth there, you want to migrate from your 10 gig or 40 gig to the higher speed, and that higher speed is basically 100 gig. Now, 100 gig is based on 4 lanes of 25 gig, right? That's from the standard. And some of the products that we have on the Catalyst 9500 that supports 100 gig, number one is this 32-port 100 gig fixed 9500, okay? That gives you 32 ports of 100 gig. We also have another SKU, which is 32 ports of 40 gig, but you can use it as a 16-port of 100 gig as well. And you can mix and match in that as well, okay? And we'll talk about that a little bit more going forward. So the Catalyst 9000 family can support a lot of different speeds and has all kinds of products to support your network. It starts with the Catalyst 9200 on the really lower end of the PERT portfolio. This is suitable for simple branch deployments. Then you have our lead access portfolio, which has 9300 and 9400. 9400 also has fiber ports, enough fiber ports to migrate your 1 gig fiber into the Catalyst 9000. And then we have the Catalyst 9500 with multiple SKUs. And then, of course, the Catalyst 9800, which is outside the scope of this session. OK, any questions so far? You guys are very quiet. Usually in my session, I have a very interactive session. So I'm going to tell you something. If you guys ask me a good question, I have some giveaways here. OK? And those of you guys who have been in my session before, you guys probably can guess what it is. One of the giveaways is the UADP ASIC, right? So if you get one of these, this is a UADP 1.1, which means you can at least build a 3850 out of this, okay, a 48 port. Okay. I also have a couple of books with me. This is the Catalyst 9000 book. Okay. So good questions and good answers earn prizes. Okay. All right. Let's keep going. So let's talk about the stackable access portfolio. Okay. In the stackable access, we have two platforms now, the Catalyst 9200 and Catalyst 9300. Let's start with Catalyst 9300. The Catalyst 9300, I'm going to be quick in this session because this is just an introduction, and then we'll go deeper dive in the next section. The Catalyst 9300 has different types of SKUs. The data-only SKU, which has no PoE. Then we have the PoE and UPoE SKUs, and then we have multi-gigabit SKUs. Okay? We also have multiple types of uplinks, 4x 1 gig, 8x 10 gig, 2x 40 gig, and this is the new one, 2x 25 gig, as well as 4x multi-gigabit. Okay? So this is the portfolio that we have. Catalyst 9300 supports stack-wise 480. How many of you have Catalyst 3850? OK. That's a good portion of the crowd. Similar to Catalyst 3850, we have stack-wise 480 on 9300. In fact, the stacking cables, you can actually reuse it here, right? So it's the same stacking architecture. The stacking architecture has not changed. We also have stack power, which adds redundancy at the expense of no additional footprint. And we have larger buffers and scales on the Catalyst 9300. Okay? On the multi-gigabit portfolio, we have three types of products. We have three SKUs. Number one, this is a 48-port SKU with 2.5 gig of 36 ports and 12 full multi-gigabit ports. When I say full multi-gigabit ports, that means it can support speeds up to 10 gigabit, 10 G base T. Okay? And this also supports a speed of 2.5 and 5 gig if it is full multi-gigabit. So the last 12 ports is full multi-gigabit. Rest of the 36 ports is 2.5 gig. Then the second SKU that we have here is 5 gig SKU. So this is a multi-gigabit port, but the maximum speed on each port is 5 gig. It can also run at 2.5 and 1 gig. This one is a 24-port SKU and can run at all the speeds, so full multi-gigabit. Now, multi-gigabit ports can also run at 100 meg. Okay? Anybody has 100 meg end devices? I always see some hands up. How about 10 meg end devices? Well, I still see a few hands going up. The multi-gigabit ports does not support 10 meg. However, the 1 gig port in the same SKU, if you have a SKU that has 1 gig and multi-gigabit, that 1 gig port will support 10 meg. But the multi-gigabit port will not support 10 meg. Okay? And then we have this module of 4 port of multi-gigabit. Just remember that there's no PoE on this one. On the power supplies and fans, we have redundancy from power supply and fan perspective, 1+1 redundancy. And we have the stacking, which is very similar to the 3850 and comes in 0.5 meter, 1 meter, and 3 meter options. So that's the maximum you can go, right? But it's very similar to the Catalyst 3850, or the same as Catalyst 3850. Now let's talk about Catalyst 9200. Question?
Excuse me, is there any plan to put SFP models on the 9300?
So the question is there any plan for SFP models of the Catalyst 9300? There's plans. I can't comment on timelines. This is not a roadmap session, by the way, right? So we don't talk about roadmaps here. I would just say that stay tuned. It shouldn't be too far. OK? What will be the next question? Next month? I'll leave it at that, OK? But it shouldn't take too long. All right, let's talk about Catalyst 9200. So we just introduced the Catalyst 9200. Catalyst 9200 has all the features of intent-based networking, and we are extending that to the rest of the to the simple branches and smaller deployments as well. Okay, so that supports software-defined access. Okay, the Catalyst 9200. It has some limitations, but from VRF perspective, for example, the scale is lower, but it does support software-defined access. Now, the Catalyst 9200, unlike the Catalyst 2960, which was its predecessor, it supports 30 watts on all ports. It has full PoE+, okay? Which means you can do all the voice, video, and access points, because some of the access points today, they require 30 watts of power. You can do that on the Catalyst 9200. Catalyst 9200 has dual redundant power supplies. And these are modular as well, unlike the 2960, which means if one of your power supply has to fail, you don't have to RMA the box. You can just replace the power supply. Okay? It gives you 1+1 redundancy. It can also run in combined mode. Okay? The Catalyst 9200 can stack up to 8 units, and it has the same architecture that we have on the Catalyst 9300, except that it comes with 160 gig instead of 480 gig. But it does have active and standby, which is very unique in this class of product. It has full SSO in this class of product, right? This is the first time we are doing on the Catalyst 9200, which means if active has to fail, the standby is going to take over in sub-second interval, and it is going to continue running the control plane as well as the data plane on that switch. Okay? Now, the Catalyst 9200 has two types, the fixed SKUs and the modular SKUs. We call it as 9200 and 9200L. The 9200 is fully modular, which means it has modular power supplies as well as modular fans. The 9200L has fixed fans. And on the front side, the modularity is on the Catalyst 9200 from uplink perspective. So the uplinks here are modular. The uplinks on 9200L is fixed. Question?
What is the reason that we can't stack them together, the fixed and the modular systems?
So the question is why we cannot stack the modular and the fixed systems together, because it is running different stacking speeds. This is stack-wise 160. This is stack-wise 80. Okay? And so it's a bit different stacking that we have on the Catalyst 9200 and 9200L. Okay? The Catalyst 9200 also gives you better scale and performance. From uplink perspective, we have two types of uplinks. We have 4x1 gig and 4x10 gig, right? On the 9200L, we have the same uplink options, except that they are fixed. And from fan perspective, we have just talked about modular fans on 9200, fixed fans on the Catalyst 9200L. Similarly, stack-wise to your earlier question, 160 here and 80 here, right? That's the total stack speed. The cables, though, are the same. It has only one ring compared to the 3 rings that we have on the Catalyst 9300. Now, Catalyst 9200 comes with shallow depth, right? So for those deployments where you have smaller racks, shallow depth, you can utilize one of these. So 13.85 on the 9200 and just under 1 feet on the Catalyst 9200L. Okay? So this is a quick summary of the Catalyst 9200. We have multiple SKUs. The 9200 has SKUs, which is basically the full PoE plus and the data SKU of 24 port and 48 port, and you have the modular uplink option. Here we have a little bit more because we have fixed uplinks, so you can basically have the same options as here, but we have fixed uplinks, and that's why there are more SKUs there. Okay. Yes, question?
Actually, I have 3 questions. Probably was on your earlier slide, but does that mean that, because I didn't see it on the pictures, the 9200 does not have local storage capability for containers of third-party apps?
Good question. So the question is, the Catalyst 9200 does not have storage capability and application hosting? Yes. The Catalyst 9200 does not support application hosting, and we'll talk about it going forward.
So moving on to that, that means it's got a different UADP inside the switch?
It has the UADP, so, and we are going to touch on that, but the UADP ASIC is different in different platforms, but it's all UADP family, which means the same architecture. Based on the platform that we have, it is going to be different based on the performance and scalability, right? So on the 9200, we have what we call it UADP 2.0 mini, okay? And we'll talk about that. Just hold on to your thought on the UADP ASIC. I'll cover that.
The very last one, if we start using and adopting DNA, what is my limitation on the 9200? Because I take it it won't act as a border node.
Border node as a Catalyst 9200?
Yeah, I take it that won't be supported.
No, that's not supported.
Just a 9300.
That's correct.
Okay.
Yes. Okay. There was another question here.
Is there a same image on the 92 AIL?
I'll cover that. Just hold on to that. Yes, I'll cover. It's not exactly the same image. It's the same base code, but it's not exactly. I'll cover that. Just hold on to that. Okay. So Catalyst 9400. The Catalyst 9400 has 3 different types of chassis: 4 slot, 7 slot, and 10 slot. Right. That's easy. I won't go into too much details there. Now, the Catalyst 9400 is based on UADP 2.0, and UADP 2.0 or 2.0 XL has 240 gig. Each one of the supervisors has 3 ASICs, and that gives you 720 gig of total bandwidth, right? So there are 3 ASICs that gives you 720 gig of ASIC bandwidth. Each of these slots are capable of going up to 480 gig, right? Which means if you have a good enough supervisor and a good enough line card, you are basically going to be line rate on all ports, right? You can't probably have more than 48 ports of 100 gig, right? Whenever it comes. But each of the line card slot is capable of 480 gig, okay? Also, the Catalyst 9400 chassis are capable of 4800 watt per PoE slot, which means now that we have the 82.1 BT standard, which supports 90 watts of power, we can introduce a line card, and the chassis will have no limitation. You just have to replace the line card, and you can start getting 90 watt of power on every single port, right? So that capability is there as well. All right. We talked about that. Now, the supervisors, we have 3 types of supervisors. We have Sup 1, which is suitable for the access, that can give you 80 gig per slot, right? We also have Sup 1 XL and Sup 1 XLY, which can be suitable for certain access, but it's also suitable for a smaller distribution and core. If you have fiber line cards, if you have 10 gig line cards or 1 gig line cards, and you want to go higher bandwidth in the distribution or core, this can give you additional bandwidth. So these 2 line cards gives you up to 240 gig of bandwidth per slot on the 4 slot chassis, and then 120 gig on a 7 slot chassis, and 80 gig on an 8 slot chassis, or sorry, 10 slot chassis, okay? These 2 supervisors also come with additional templates, which are more suitable for SD access border, and NAT and certain other features, okay? The SOUP 1 XL comes with the same uplinks options that we have on the SOUP 1, but the SOUP 1 XLY comes with the 25 gig option as well. Yes?
If I use the 10-slot chassis and only insert 4 slots, I'm limited to 80 gig, or then I'm able to use the 240 gig?
Good question. So the question is, if in the chassis I have a 7-slot chassis, but I'm using only 3 slots, am I going to get more bandwidth? Your bandwidth is dependent on the chassis. It's not dependent on the number of line cards that you're using, because you have to program the supervisor based on the chassis that you're using. So it's already programmed in the back, how many lanes it is getting from the chassis to the supervisor. Okay? All right, so let's talk about the supervisors. So we have multiple options here. The first option on the uplink is that you can use all the 8 uplink ports. You can also use the 40 gig ports, okay? Now you also can mix and match. So you can use 4 ports of 10 gig and 1 of the 40 gig ports. The thing to remember here is that you cannot go, just because you have more ports here, you cannot go more than 80 gig of uplink bandwidth on any supervisor today, right? All the supervisors that we have, the maximum bandwidth that you can get on it is 80 gig, okay? If you have dual supervisors, the 80 gig limit doesn't change. It stays the same, right? It's a centralized architecture. Dual supervisor gives you redundancy. It does not give you additional bandwidth on the uplinks, okay? So that means you can use 4 of the top 10 gig and 4 on the bottom one, or you can use 40 gig, 1 on each. You can use that. You can also do mix and match, right? So you can use 10 gig here and 40 gig here. That's possible. On the 25 gig, you can use all the 10 gig ports. If you are using the 25 gig port, the first port that you have on each of the group of 4 can be used as a 25 gig port. When you use the 25 gig port on this group of 4 ports, the rest of the 10 gig ports gets disabled. Okay? Yes? You can mix and match. You can mix and match as well. So you can go and use one of these as a 25 gig port and use a 40 gig as well, right? But again, you can never go more than 80 gig. In this case, it will be less than 80 gig because if you are using the 25. Yeah, you can use 125 and the other 410. Yes, you can use that. Okay. On the line cards, we have the Ethernet line cards with data only, PoE, and multi-gigabit. The multi-gigabit comes with 24 ports of 10 gig and 24 ports of multi-gigabit. Okay. Then we have the fiber line cards, which is basically the 48 port of SFP and 24 ports of SFP, as well as 24 ports of SFP plus. That can give you 240 gig total if you are using 4-slot chassis, right? Line rate. If you are using 7-slot or bigger chassis, then it might not be line rate, right? So we talked about that. From power supplies perspective, we have modular power supplies that can give you up to 8 option for 8 power supplies, depending on what you need. And it comes in 3200 watt as well as 2100 watt with a 16 amp circuit or a 10 amp circuit, right? So you can use that based on what you need. From power supply perspective, we have the combine mode as an option. So you can combine all of those power supply and get the PoE out of it, right? So you have that option, or you can have the redundant option, which means you can have some power supplies as the primary power supply and one or more power supply as redundant option. So if one of these power supplies fail, that one take over. Yeah.
Are there 48 volt power supplies direct current, DC?
DC power supply? There's no DC power supply today. Yeah, we don't support it today. Okay, but we might be supporting in the future. We are working on it. Okay, when it comes to redundancy, there are two types of redundancy. You can have an N+1 redundancy, which is, I think we are familiar with. So you can have basically multiple ports and one power supply, multiple power supplies and one power supply for redundancy. Or what you can have is you can have the N+N redundancy, which means you can have 4+4. So you can have the 4 going to the UPS circuit and the other 4 coming from your provider, right? You can use that as well. Now, Catalyst 9500 series has two types of SKUs. One is based on Catalyst and UDP 2.0, and the other one is based on UDP 3.0. Okay? Now, we'll talk about that a little bit more. The UDP 2.0 XL SKUs are the 12Q, 24Q, 40X, and 16X, right? And these are 40 gig and 10 gig SKUs. These come with this one, the 40 ports of 10 gig. This one comes with an uplink option, and those uplink options has the option for 2 ports of 40 gig and 8 ports of 10 gig. Okay, it comes with dual fans and power supplies, redundant fans and power supplies, so dual power supplies and N+1 fan redundancy. The high performance SKUs come with 4 different SKUs. The Catalyst 9532C is a 32 port of 100 gig. Then we have the QC, and then we have the 25 gig. Let me explain a little bit more on this one. So the 32 port of 100 gig comes with 100 gig. Each port can be used as a 40 gig as well. Okay? The next one is 32 QC. I'm going to explain a couple more points here. But basically, if you disable one of the top ports or one of the bottom ports, you can use the top port as a 100 gig. Okay? And you can mix and match. And then we have the 225 gig. These can be used as 10 gig as well. So you can start with a 10 gig, go to 25 gig. And if you're using a dual rate optics, that's more future proofing. Now these come with dual redundant power supplies as well. And we have N+1 redundancy in fans. Yes?
One question for the buffer. You said that it's written that unified buffers for all ports.
Say it again?
You said on the previous slide that it's written that there are unified buffers for all ports or packet buffer.
Yes.
How does this behave with microbursts?
Good question. So the question is, how does the shared unified packet buffer deals with the microburst? So on the UADP 3.0, and we haven't reached there yet, but on UADP 3.0, we have a much larger buffer compared to the UADP 2.0 and 2.0 XL. Okay? And it's a shared buffer across the 2 cores, but we haven't covered the architecture of the ASIC yet. But shared buffer of 36 meg obviously gives you a lot more room for bursty traffic, right? Much more than the other 9500 that is based on the 2.0. Okay? Now, how much you can exactly get, that really depends on multiple factors. So we can take that offline probably. But it definitely gives you a lot more buffer compared to the 9500 that are based on 2.0. Okay? Any other questions? Okay, so we talked about the redundancy in fans and power supplies. Let's talk about the fans and power supplies on some other SKUs. So this fan and power supply is for the 32C SKU. We have a slightly different architecture when it comes to the other 9500 high performance. And those are, we have 2 fan trays, right? Each one of them has 1+1 redundant fans. And then we have redundant power supplies as well. Because 32C is based on 2 ASIC, it needs better cooling. And that's why we have slightly different fan architecture on the 32C versus 32QC and rest of the high performance SKUs. Now let's talk about this 32QC. It's a little interesting how we have done the port speeds. So when you receive a new 9500, the default that you get is this one, which is basically 40 gig on the first 24 ports, and the last 4 are 100 gig. The top ones are 100 gig because the lower ones are disabled. Okay? That's the default configuration. But what you can do is you can run it as a 40 gig on all ports as well. And what you can also do is you can run it as a 100 gig on the top ports, and that's 16 ports. But you can mix and match as well. Okay? And it's very easy to enable the 100 gig. If you have to enable 100 gig on any pair of port, you just enable it on one and it gets disabled on the lower port, right? So if you enable 100 gig on a top port, the lower port gets disabled. So what you can do is you can selectively take maybe some of the ports for 100 gig, some of the ports for 40 gig. You can mix and match the way you want. Okay? All right. Now, the Catalyst 9500s also have some breakout options, right? I usually hear the questions about the breakouts on the Catalyst 9500. And so let's talk about that a little bit. Now, the breakout options came in pieces on multiple releases, okay? So the first one here is the 32C. On the 32C, we have the option to break into 4 of 25 gig or 4 of 10 gig. You have both options available. Now, if you see this green rectangle, this means this came in 1610 release. Okay, this is ISXE 1610. Some of these things have come already in 16.9 and 16.8. So if you look at the 24Q, on the 24Q, we already had support. We started with 2 ports or 4 ports of 40 gig to be broken up into 4 ports of 10 gig, and then we have additional breakout support. Similarly, on the 12Q, now we have support here as well. On the 40X and 16X, we do have breakout support on the uplinks as well. Okay? So that's a quick summary of the breakouts. How many of you are familiar with the QSA option? Okay, question. 40 to 10?
10 multiplied
10 by 10? On a 100 gig, you mean? Yes. No, that's not possible. Because the 100 gig standard is based on 4 lanes of 25 gig. We cannot break it into 10 100 gig. Yeah, so it really depends on the architecture, but the architecture that we have is based on 4 25 gig lanes, right? So it cannot be really broken into 10 gigs, okay? All right, so the QSA adapter is basically an adapter that converts your 40 gig or 100 gig ports into a 10 gig port, right? So it's an adapter. It will give you just 1 port, but it's a 10 gig port. So there are different options available for the QSA adapter. The 32C and QC are supporting the QSA option, as well as the uplinks on the 25 gig SKUs. We also have support for QSA on 24Q and 12Q, as well as on the uplink options. So it's pretty much fully covered. Okay, so we have talked about the high level so far. How we are doing on time? Okay, we have about 1 more hour. So we have covered so far the introductory part, right? There's a lot of different 9K products. We have talked about high level. What we are going to do now is we are going to go a little bit deeper and look inside these boxes, what is the architecture, and what are some of the ASICs that we are using, right? And that gives you a very good overview of what they are capable of. When we say it's line rate, what that really means. when we say there is a limitation, what that really means. So let's dive into that. Now, in general, the architecture is twofold. It's a fixed architecture on the fixed boxes, and then we have some of the modular boxes. So 9400 is the modular box. Rest of the boxes are fixed, which is 9300, 9200, as well as the 9500. Now, the fixed architectures are simple architectures. There's just a pizza box. You just put the board in there, and top of that you have some ASIC, and you attach the ports. Right? There's no modularity from the architecture perspective. So if you open the box, I won't advise you to open this because that will disqualify your warranty, right? But if you open this, you'll see something like this here. You will see a lot of different components, different electronic components in there. The key component that you have, where most of the processing happening, is the UADP ASIC, right? So you will see two big heat sink on top of the ASIC. You won't see really the ASIC itself, but you see the heat sink on top of it, and that's where most of the processing happening, okay? Now, if you have to lay this out in a block diagram, you will see something like this, which is basically the different ASICs that we have and how they are connected. So you start from the front panel ports. You have a group of 6 ports connected to different physical layer, right? These are the PHYs. PHY is nothing but a small electronic chip that does the modulation and signaling for the traffic that is coming in, right? So that's the first component that takes the traffic in and sends it to the ASIC. Now, the ASIC takes that traffic and sends it to the destination port, right, after processing it. And we'll see how we process it. But basically, it goes through the ASIC and ASIC cores. And if the destination port is on the same ASIC, it will just come out of that same ASIC. If the destination port is on a different ASIC, it has to take some other path. Excuse me. If it has to take another path, how does it take? We have usually some inter-ASIC connectivity, either with a stack ring or cross-connect. There are different types of back-end connectivity for ASIC to ASIC connectivity, and that's what the packet takes. That's the path of the packet. So it takes that path, goes to another ASIC maybe, comes down here, and then goes out. Okay? Now, if you go to the 9524Q question.
Is it possible to repair defect RAM?
Is it possible to repair defected RAM? Yes. The RAM is, you can, okay, so you can probably repair it, but you have to RMA the box, right? There's no option for the customer to kind of replace it. It's a fixed RAM, okay? Now, 9524Q has this layout, which is basically has 4 ASICs, right? And each ASIC has 2 cores, right? So this is a little bit deeper view. In each of the ASIC, there are multiple components, and once we go to the ASIC section, we'll see what are some of these components inside. But basically, these are 4 ASICs that you can that you have, and each of the ports, ports 1 to 6 are connected to each ASIC. Okay, the 32C, which is based on UADP 3.0, has a very similar layout, but the ASICs that we are using is 2 ASICs. Okay, and these ASICs, so this is one ASIC. It has 2 cores, core 0, core 1, and then another ASIC with core 0 and core 1. And then the network interface is basically the interface that connects to the PHYs and to the front panel ports. So this is your QSFP28, which means 2 ports of 100 gig getting connected to the PHY, and that PHY is taking the traffic to the network interface, and that network interface is taking traffic inside the ASIC and getting it processed. Similar to the 24Q, we have a backplane which connects the two ASICs. Now in this one we have 2 rings. We have 2 400 rings going from each ASIC to the other ASIC. Okay? So that's 800 gig that you have from ASIC to ASIC. All right, the 32QC is based on just one ASIC. It is 1.6 terabit ASIC. So it will give you basically line rate on all ports with just one ASIC. So this is very simple. Every port is connected to the same ASIC. There is no backplane because there is just one ASIC. And it still gives you a full line rate on all ports. Okay? Now, if that was 9500, different types of 9500s with different ASICs. We have seen that. 9300 is not any different. Depending on the SKU that you have, you might have one ASIC or multiple ASICs. In your hidden slides, you will see a lot more layouts, but I'll explain one, and the others are just very similar. So on the 9348 port, this is 1 gig SKU. It has just one ASIC. This ASIC is capable of 160 gig, so you actually have an extra bandwidth on the ASIC because the ports are only 48 plus the uplinks. You have a lot of bandwidth available. So the ports are line rate on all ports, and the additional thing that you are seeing here is the PoE UPoE controller. So on the copper ports where we have PoE, we have this controller which basically looks at the power that you need to either transmit or you have to receive some signals about the power. So that component does that part, the PoE part. Okay? The rest of the things are very standard, similar to the other layouts. On the Catalyst 9200, it's not any different. The ASIC is different, but the layout is same. All of the ports are getting connected to the same ASIC. The big difference here is this ASIC has just one core, right? So, and we'll talk about the different types of ASICs that we have. Okay? So this is a quick overview of all of the layouts that we have for all of the fixed SKUs. Now let's talk about some of the modular SKUs. On the Catalyst 9400 side, we have the 7-slot, 10-slot, and the 4-slot chassis. I'll start with the 7-slot and 10-slot. Now there are certain components, important components that we have in the Catalyst 9400. It starts with the power supplies, right, at the top. Right? Then we have the fan trays here. We also have supervisors, and we have the line cards, right? That's what really makes the chassis, right? These are the 5 components that really makes the chassis. Now, if you look at the architecture of the Catalyst 9400, it's a centralized architecture. So those of you who are familiar with the 4500, it's basically very similar. It's not a distributed architecture. It's not a fabric-based architecture like Nexus 7K or Cat 6K, right? Centralized architecture means all of your processing is actually happening on the supervisor in a central place on a supervisor. So your intelligence is on the supervisor. That's where you have the ASICs. The line cards have just a stub ASIC to process some of the traffic, maybe deal with the oversubscription ratios, some very simple things, but no processing. There's no code, no software code that is running here. There's firmware that's running in there, but there's no software code that's running there. So when you upgrade the code, it only upgrades the supervisor, basically, right? In very rare instances, we upgrade the code on the line cards. Okay? So that's the architecture. We do have a backplane. It's a passive backplane, right? It's not an active backplane. And that backplane has 480 gig per bandwidth per slot, right? So that's a lot of bandwidth in the chassis. So your chassis is fully future-proofed. That's a lot of bandwidth that you have in the chassis. Depending on the line card and the supervisor, you can go all the way up to 480 gig per slot. Now let's look at the block diagram of the supervisor itself. So when you look at that, you will see that the UADP ASICs are connected in a ring topology, right? And that's the most important component on the supervisor. These rings are 720 gig in each direction, okay? And that will give you up to 1.4 terabit per second on the ring. So that's great. And then we have multiple links going from each of the ASIC to the backplane. Okay? So each of the line cards is getting the bandwidth from each of the ASIC that you have. And these are mapped differently for different types of chassis. So on the 7-slot chassis, we have slot 2 and 7 going to UADP ASIC 1, this one here. And on slot 10, it is going to 1, 9, and 10. And this table is there for your reference. Okay? So depending on the chassis type, you will have different cards getting connected to different ASICs. Now you have 24 lanes of 10 gig each, which means you have 240 gig of bandwidth, which is basically the bandwidth that you have on the ASIC that is going to different line cards. Depending on your arrangements of the different line cards and the chassis you have, you will get that much bandwidth, right? And I think there's next slide, you will see how do we do it on the line card. But this is the supervisor part. Rest of the components here are CPUs and other memory and different other electronic components that reside on the supervisor. Now the line card, if you look at the 48-port 1 gig line card, it's a very simple architecture. You have an ASIC called a stub ASIC, which basically takes all the traffic from these ports, send it up to the backplane, right? There are 6 SLIs. SLIs mean different lanes. So 6 means 60 gig. So you have, on this card, you have 60 gig of bandwidth in the back. And you have 48 port here, so you are line rate on all port. So the card is not limited from bandwidth perspective, okay? Now if you look at a different card, this one is the 10 gig card that we have on the 9400. On the 10 gig card, you have 4 stub ASICs. Each stub ASIC is transmitting 6x of 10 gig. That's 240 gig. The card comes with 24 ports of 10 gig ports. And with these lanes, you are line rate on all ports, right? So from the line card perspective, you are line rate. Now it depends on your chassis that you are using, excuse me, and the supervisor that you are using. And based on that, you may or may not be actually line rate. But there's no bottleneck in the line card itself, right? If you are using a 4-slot chassis, for example, you will be actually line rate because you are getting 240 gig on every line card. But if you are using a 7-slot chassis and you are using a SUP1 XL, that will give you 120 gig on the same line card, and you will be 2:1 oversubscribed, right? So you really have to, it's a modular system, right? Which means you have to, you cannot just look at one line card and say if I'm line rate or not. You have to look at all components, and these are 3 important components that you need to look at. Number 1, line card, if it is oversubscribed or not. Number 2, supervisor, if it is giving you that much bandwidth on each slot or not. And then the chassis, which means in the passive backplane, you have enough bandwidth or not. So from chassis and line card perspective, you are all good, right? It has a lot more bandwidth than you need. The only thing that you need to then look at is the supervisor and how much bandwidth it is giving you for the type of chassis you are using, okay? All right, now let's go and talk about the UADP family. Okay. Now ASICs are our pillar of Cisco innovation. And Cisco invests a lot of money and a lot of resources into ASICs. And you probably have noticed that we have been doing custom ASICs, while we have option to go to merchant ASICs as well. And that has given us a lot of advantages, right? It's a lot of investment, but at the same time, we get a lot of advantages by doing the custom ASIC. Now, I talked about the UADP ASIC briefly earlier, but I'll double click into that. ASICs in the networking industry they have been a very fixed piece of hardware, right? If you go back 20 years and you come to 2015, for example, or let's say 2012, there was no change in the ASIC from architecture perspective. It used to be a fixed ASIC 20 years back. It was still fixed ASIC in 2012. If you look at the other industries, like the video industry, for example, they have changed. They have made different types of ASIC that could have been programmable. And the traditional ASIC, when we say it's a fixed piece of ASIC, what does that really mean? That means when the packet comes in, it looks at the ASIC header, at the packet headers, right? And it goes through something called fixed parser. Fixed parser is a component in the ASIC that basically parses the packets, okay? It basically reads the packet. But this is a fixed parser, which means it can only read a specific type of headers, right? That's what we used to have. So if you have 4 types of different lookups that you want to do, this ASIC is built for that. It can do it. But if you have an IPv4 header here, and now you are introducing an IPv6 packet or feature, can this ASIC support it? No. Because this ASIC was never designed for IPv6. This ASIC has no component called IPv6 lookup, right? And you cannot change it. It's a very fixed piece of hardware. And the advantage of having a fixed piece of hardware is it has a lot of performance, right? It gives you line rate performance, 200 gig performance, 400 gig performance, right? So that's the advantage. But from flexibility perspective, is it flexible? No. So what happens when we introduce newer headers, VXLAN, GRE, MPLS, now we have to support it, what do we do? You will hear something, we say, it's not supported in hardware. That's what it really means, right? It means that this platform, this ASIC, was never built for that, right? So it's not going to support it. So what's the alternative? Build a new ASIC, right? I mean, if the ASIC was not built for a specific header and it doesn't support it, what you are going to do? You are going to go and build a new ASIC. The only problem is that ASIC development takes a very long cycle, right? 2 to 4 years typically, and sometimes it's more, right? And it goes through a lot of different phases, right? It's a really long cycle to build this ASIC. In this era, when the technologies are evolving very rapidly, this 2 to 4 years becomes too long, right? So what is the alternative? One of the alternatives that we have is CPU. CPU is very flexible, right? We all have CPUs on our PCs, right? And we can program whatever we want. The problem with the CPU, though, is it's very low in performance. There is almost no performance compared to the ASICs that we have in the networking devices. So we have on one side a traditional networking ASIC, which has very high performance, very low flexibility. On the other side, we have CPUs, which has very low performance, but it's very high flexibility, right? So in 2013, Cisco introduced this ASIC called UADP ASIC, right? In this UADP ASIC, it has all the great features of the fixed ASIC, which means it has great performance. But at the same time, we have added enough flexibility in the ASIC so that we can program to a certain extent, right? So if new protocols come out, we are able to adopt those new protocols, new headers. You don't have to create a new ASIC right from scratch, right? And that's the story behind the UADP ASIC. That's the flexibility that we have added in the UADP ASIC. Now, the UADP ASIC has evolved over time. We started with UADP 1.0 in the early 3850s, and then in the later 3850s, we had 1.1, right? And then with the Catalyst 9000 series, we have introduced UADP 2.0 and 2.0 XL that has 93. So 9300 is based on 2.0. 94 and 95 are based on 2.0 XL. And 9500 high performance is based on 3.0 XL. The 9200 is based on a new ASIC, which we have just launched, which is called UADP 2.0 Mini, right? Yes, question?
Do these ASICs have some project names or something that might appear in this one? Like Earl?
Oh, like Earl. So the question is, what are some of the internal code names for the ASICs? So this one is pretty known. Usually we don't share the code names, but for the UADP is pretty known. It's called Doppler, right? Which I think is pretty cool. But it was not my decision to name it as UADP, right? But the internal code name is Doppler, and in fact, you will see that on the ASIC as well, right? So this one has Doppler written on it, as well as UADP. Now, as you go from 1.0 to 2.0 to 2.0 XL 3.0, you will see that we have advanced in the technologies. So it has gone from 36 nanometer to 28 to 16. And we have also increased the amount of transistors that we have in the ASIC, right? So if you go and look at some of these ASICs, I have this one as 1.0, right? And this is 1.1, right? Not much difference from size perspective. But if you go to 2.0, this is 2.0. This is much bigger. This has 7 billion transistors, okay? And when you go from 2.0 to 3.0, this has a lot more transistors. It has 20 billion transistors compared to this one, which is 7 billion. But this is also based on 16 nanometer technology, and which means the size has not increased that much, right? I feel this is a bit heavy than 2.0, more transistors probably. And then the UADP 2.0 Mini is a smaller ASIC that we have that is designed specifically for Catalyst 9200 like platforms, right? The cool thing about this ASIC, the UADP 2.0 Mini, which goes in 9200, is it has an embedded CPU, okay? So this ASICs come with an embedded CPU in it. That means we don't need a separate CPU, which makes the entire platform much more lighter, less power hungry, less requirement for cooling, right? So it just makes that platform better. A platform like 9200, which is ideal for simple branch deployments, a lot better, right? And that's why we have not put an x86-based CPU, to your earlier question, on the Catalyst 9200, because the ASIC already has it, okay? So that's the story behind the UADP evolution. Now, this is a quick reference table for you. I'll skip it. It's there in your slides. Now, let's look at the architecture of the UADP ASIC. So if you look at the layout of the UADP ASIC, if you open it up and look at it, it will resemble something like this. So you have the network interface port. You remember in the layout we had the network interface port. That's where the network ports get connected, right? So that's the network interface port. That's the front panel port. When the packet comes in, it goes through this path, right? We have a few components. I'm going to talk about the packet walk in a little bit, but the key component that we have here is IFC, the ingress forwarding controller, and the egress forwarding controller. That's basically the heart of the ASIC. That's the main pieces inside the ASIC. That's where all the processing happens, right? All of those lookups that we have to do, the ACLs, access lists. Everybody deploys ACLs, access lists? Anybody deploys access lists? Yes? Those are getting processed here. The ingress ACLs are processed here. The egress ACLs are processed here, right? And where is it stored? It's stored here in the lookup tables. That's where you have all the TCAMs, okay? So that's the internal architecture of the ASIC. Now, what you have here is the packet buffer. The packet buffer complex is the complex that has the buffers. So the earlier question about the 36 meg of buffer there, that's where we have the buffer, okay? We also have what we call it a stack interface of the backplane of the ASIC. That's what connects the ASIC to other ASICs, okay? So if you have multiple ASICs in a box, that's where it connects it. It also connects it to other ASICs in a different box. So if you have multiple 9300s getting connected, and you have this cable going in the back, that cable is actually connected to this stack interface in the back of the ASIC. Okay? It's very interesting how all of this works. We also have the queues. That's where the QoS happens. That's where we have all the queues. This is a rewrite engine. So when the packet goes in the ASIC, it comes out, and it wants to go to another port. It has to update the MAC address, for example. That MAC address gets updated here in the rewrite engine. Okay? The ASIC, UADP ASICs also support MACsec encryption, right? It has the MACsec encryption capability. As soon as the packet comes in, it decrypts the packet if it's already encrypted. Then it goes as a clear packet. And if MACsec is enabled, when it's getting out, it gets encrypted again, right? So those are the MACsec engines that we have. Now, in the middle, two more things: recirculation engine and encryption engine. This is a different encryption than MACsec. If you have to do AES 128 encryption for a protocol like DTLS, you will have to recirculate the packet. It comes here and then does the encryption. Recirculation engine helps with the recirculation of the packet. There are certain instances when you have to recirculate the packet, meaning the packet comes into the ASIC once, gets processed, it processes some of the headers, but then it needs to look deeper into the packet, so it goes through one more pass, right? And that's what's called recirculation. Yes?
What about IPv6 packets? Do they need to do a recycling or not?
Good question. So the question is, does IPv6 packets need recirculation? In this ASIC, IPv6 packet does not need any recirculation. We process it in one pass, and the IFC and EFC are capable of handling it. Okay, so that's built in. All right, now let's look at some of the key features. I'm going to be brief on some of these, and we'll go into the first one and deep dive into that. When you look at the capabilities of the UADP ASIC, the flexibility and programmable pipelines, that's where we have the programmability of the ASIC. That's one of the key features of this ASIC. I'm going to double click into that. We also have recirculation capability. Okay? So we just talked about the recirculation engine, which gives this UADP ASIC power to handle different types of packets, because once you have the recirculation capability, you can pass it once, but then pass it again for processing another pieces of the packets. It also has, it's very flexible, but it also has certain micro engines, which are very fixed. So it has micro engines to process your net flow, for example, and access list searching, for example. There are multiple of these engines that are sitting there and doing specific functions in the ASIC. And then we have adaptable tables, which means these tables can be carved in different ways, right? We talked about that briefly early in the presentation. So let's talk about the first one here. The programmable pipelines that we have are inside the ingress forwarding controller. And we talked about this slide earlier. I'm going to open this piece of the ASIC a little bit more. Okay? So when I open this up a little bit more, you will see you are basically seeing inside those components. And what you really see inside these here is have you guys been to some factory tours? Have you guys seen any supply chains, how factories operate? They basically have some raw material coming in, right? And they go through different cycles or different stages. They get processed, and at the end of the supply chain, they get out, right, as a finished product, right? I'm pretty sure some of you have seen it or are familiar with it. The packet processing is a very similar scenario, right? It's a very similar phenomenon. When the packet comes in, it goes through certain stages to get processed, very similar to a factory, right? So this goes through multiple stages, and we have 17 stages in the ingress. At each stage, it does two things. It does a lookup, and it does a processing of the packet. When the packet comes in, what happens is we take the first 256 bytes of the packet and throw the rest of the packet out. But before we throw it out, we also copy that copy another packet and put it in the buffer that we had, in the packet buffer, okay? So the packet, the original packet is stored, and now we are processing just the headers. So the header basically goes through the different stages. At each stage, some of these stages are processing ACL, some of these stages are processing QoS, NetFlow, policing. All of these stages are doing some certain functions, okay? Once it gets to the last stage, goes through this component called IGR, which is basically the decision maker. This decision maker takes that final packet that it has a lot of descriptors on it and looks at the packet and makes a decision whether this packet needs to be forwarded or dropped. And if it needs to be forwarded, where it needs to be forwarded. Based on that decision, it takes the packet and puts it either drop it or puts it in the forwarding path. When it comes to the egress path, which is the, on the destination ASIC, it could be the same ASIC as well, it goes through a similar processing. But you see here, we have 17 stages. Here we have only 8 stages. Anybody knows why? Why we have 17 more stages in the ingress versus less stages on the egress? You can get an ASIC. Any guesses? Okay, yes.
No forwarding decision to make?
Say it again?
There's no forwarding decision to make?
Yes, that's part of it. Thank you. You'll get an ASIC. There is no forwarding decision that needs to be made on the egress. Most of the decisions that needs to be made is on the ingress. So your L2 lookup, L3 lookup, most of the lookups are happening here. So what are some of the egress processing that we need to do? Your egress access list. You know when you do the IP access group out? You guys probably have done that, right? When you do that out, that is processed here. When you do the in, that's processed here. But if you look at your features, the features that you apply on the ports, for example, most of those are on the ingress side, right? We have some features on the egress side, but most of the processing happens on the ingress side, and that's why we have more stages there. Now, each of these stages is programmable. So if, let's say stage number 2 is today is processing VXLAN for SD access. Tomorrow I can change it to maybe BGP, VPN, right? That capability is there in the ASIC, and that's the power of the UADP ASIC, okay? All right. So let's go, and so with these programmable stages, now I'm talking about all these benefits. What is the proof that we are actually getting these benefits? One of the proofs that we have, we can easily see on the Catalyst 3850. When we introduced Catalyst 3850 in 2013, we have certain amount of features that were hardware, that were getting hardware processed, right? And it was pretty standard features for a switch like 3850. When we moved to 2015, we had a lot more features. We had a SPAN, SGT, multiple features that were coming on the same Catalyst 3850 that you bought in 2013. Later on, in 2017, 2018, we introduced the SD access. And now we are able to process a lot more features. We have MPLS, VXLAN. This would have not been possible if we were using the same fixed ASIC architecture 10 years back, right? And that is the power of the flexibility and programmability of the ASIC that we have. All right. The next thing is recirculation engine. The recirculation engine is here, right? And what it really does is it recirculates the packet. It goes through this cycle, and when it comes here, it makes a decision that it needs to go through the second pass. That's where it goes to the recirculation path, and then again it applies the different policies, go through the ingress forwarding, egress forwarding, and out, okay? So that's a quick overview of the recirculation path. Question?
How does the recirculation affect the overall throughput?
Say it again?
How does the recirculation affect the overall throughput of these?
Very good question. Actually, for that, I'll give you an ASIC. So the question is, how does recirculation affect the performance? So there are two pieces to it. There is a forwarding performance, and then there is a delay. Right? There's forwarding performance, which is in bandwidth, and then there is a latency that gets added when you do recirculation. So the forwarding performance does not get impacted if you have additional bandwidth in the hardware, right? If your hardware has extra bandwidth in it, and you are, for example, the hardware has 100 gig, the ASIC has 100 gig, 2.0 mini, and you have 48 port that's coming in. So you have additional 50 gig remaining there. You can recirculate the packet. There's no impact on performance. But there is an impact on latency because now the packet has to spend one more cycle here inside the ASIC. So the packet is still in there. So the latency gets added. The latency in the UADP ASIC for each pass is half a microsecond, which is negligible in an enterprise network. It really doesn't add much latency, right? So latency gets added. It's half a microsecond. Depending on how many recirculations you are doing, it will add half a microsecond latency on every recirculation. Now, I have seen scenarios where it goes up to, you can do up to 15 recirculations, by the way, in this UADP ASIC, right? I have not seen that crazy recirculations. I have seen up to 7. Okay, 7 is possible. If you have, for example, GRE and MPLS and multiple different headers that you need to process, you could go up to 7, right? And that means you are adding 3 microseconds of latency, okay? All right, so let's talk about software a little bit. The OpenIOS XE, when it started with the iOS used to be a very monolithic operating system, right? It used to have a big blob of code. And over the years, we have added thousands of features, and those thousands of features got added in a very monolithic way. There was no modularity. About 10 years back, when we started the iOS XE 3.x strain, we started modularizing it. And what we did is we started running a Linux kernel. On top of that, we have made this iOS as a daemon that is running as a daemon. That was the first phase. What the advantage that has given us is now we could have run other hosted applications as well. And one of the examples was the Wireshark, right? How many of you have used Wireshark on Catalyst 4500, right? So that's the example here. That's how Wireshark is running. It's running as a hosted application, as a daemon on top of Linux kernel. In the iOS XE 16, we have advanced the operating system in a different way. Basically, what we have done in the last 5 years, we have started thinking how we can re-architect iOS into a modern operating system that can handle the Yang models, for example, that can handle the APIs, that can handle Linux containers. And so we have added three key components. One is IOSD blob was broken into multiple iOS subsystems, right? Second is the Linux containers support on the operating system itself. So now you can host different applications. And the third is the iOS XE database. Basically, that holds all of the data that you have in the code inside a database. And what that means, if one of the iOS subsystem has to fail, your data is still there inside the iOS XE database. So your data remains intact. Your code can fail, but your data is protected. And that's where we are able to bring features like hot patching. Hot patching is a feature that is available today on Catalyst 9K, right? Which means you can apply a fix, apply a patch on the software without reloading the box, right? That would have not been possible if we did not have this architecture of iOS XE database and iOS subsystems. Now that we have more modular operating system with iOS XE database holding all the states, you don't lose the data. You just patch it, the code, you update the code, and get the fix. Now, one of the cool things that we got out of the iOS XE operating system is we are able to bring consistency across the platforms. Other than Catalyst 9200, all of the Catalyst 9K that we have, Catalyst 9300, 9400, 9500, all types, they all run just one image, right? It's not just one code base, it's actually just one bin file that you have to download. You can download a 9300 bin file and run it on 9400 and 9500. That's a huge value add for our customers because now they don't have to maintain multiple copies of the iOS, and they just have to certify one image. You don't have to go and certify multiple images for each of the Catalyst 2K, 3K, 4K, 6K. Every Catalyst used to have a different image. So iOS XE 16, it is the same base code across all product lines, 9200 included. But on the 9200, because we have a smaller memory footprint, right? It's a smaller box for simple deployments. That's why we had to make a smaller image, an image that is smaller in size that can fit on that smaller memory footprint. So for this one, we have a different binary image. For rest of the systems, we have the same binary image. Yes?
So what about ACI-capable switches? Is it just a software then? Is it the same image that's being used, or is it completely different software?
That's a completely different software.
Completely different
Yes.
software. And if you have a switch, if you order one in native NXOS mode, and then you want to upgrade that later to ACI, given that it's capable, will the ASIC get reprogrammed as well, or?
I am not sure. So I'm not sure on the Nexus side. Yeah, that's the Nexus side of that's on the data center side. So I usually deal with the Catalyst switches. I am not 100% sure on how their architecture work. That will be a better question for somebody from the DC side. Okay? All right, so that's the iOS XE architecture. Now let's look at some of the high availability features that we have on the Cat 9K. From high availability perspective, one of the most asked features, and most of the people are interested in this, is the Stackwise Virtual, right? How many of you are familiar with VSS? VSS on 6K, 4K? Okay, most of you are familiar with VSS. Stackwise Virtual is an enhanced VSS in some ways. It's the same thing, right? You are achieving basically the same thing out of the Stackwise Virtual as you are getting it with VSS. There's no difference, okay? We have made some of the commands simpler. It works with more features. For example, VSS never worked with MPLS on 4K. Now you can use it with MPLS as well, and some other added benefits. But from functionality of the Stackwise Virtual perspective, it's exactly the same as VSS. So since you guys are familiar with VSS, I won't go into explaining what it is, but basically it will give you redundancy in your aggregation layer, right? You can dual home your access and use multi-chassis Ether channel. Okay, so I will keep it short. On the Catalyst 9300 side, we have a Stackwise 480 with active and standby. What we really have is a centralized control plane that is running on active and standby, right? A standby is running as a hot standby, which means it has a continuous sync of the states of the control plane on the standby. So if active has to fail at any point, standby takes over within sub-second, right? That way you don't have any outage from control plane perspective and data plane perspective, unless that data plane happens to be on the active. In that case, you are going to lose that port. But you can stack up to 8 members and have 1+1 stateful redundancy. SSO and NSF is supported. The Catalyst 9K also support, yes?
One question back to the stack. Do I need dedicated stack cables, or can it be done like with the VSS?
You need okay, so the question is, do we need dedicated stack cable? Yes, you need dedicated stack cable for Stackwise 480. Okay? For Stackwise Virtual, you don't need that. Of course, you can use it with a fiber cable. So the Catalyst 9K also supports ISSU, and this is supported today starting 16.9 on the Catalyst 9400, as well as on the Catalyst 9500 with the Stackwise Virtual. Okay? So that is supported, and it's a very simple process, a 3-step process. You can also do it in a 1-step. But if you are familiar with the Catalyst 4500 ISSU, it's a very similar feature, and it will give you basically 0 downtime to upgrade your box, right? So if you have 2 supervisors, you just execute these commands or one command here, and it will upgrade the standby, go back to the active, upgrade the active, and then switch it over, right? This is like if you are running a video during this process through this box, you won't even see a glitch, right? That's how seamless it is. Now, one quick comment on the ISSU, which is ISSU is only supported on the major releases. So it's supported in 16.9. Next, it's going to be supported in 16.12. It's not going to be supported on standard releases. Okay? So that's something to keep in mind. Stackwise virtual, very similar, but it's basically between the 2 peers of the stackwise virtual. But the process is basically the same. You can upgrade the 2 boxes with your traffic still up and running, right? You will get part of the network down here, but at that same time, you have dual links, and the standby will take care of the traffic. So you don't really have that, the downtime, full downtime. We also have what we call it GIR. The GIR is a feature which is an abbreviation for graceful insertion removal. So when we have L2 or L3 network in our systems, and we have to upgrade one of the boxes that is sitting in the middle in the distribution or core, if we have to take that box down, what do you typically do? You shut down the box, right, going for maintenance. And what happens to the traffic? It's not graceful. This shutdown is not graceful. So the traffic basically drops, because there is some traffic coming here at that time. You shut this down, that traffic drops. So you have some disruption in the traffic. With the GIR, what happens is the traffic that is coming either from the access or the core, if you put this distribution box in GIR mode, it will gracefully take the traffic from your alternative path, right? And once the traffic has completely gone to the alternative path, then you can bring the box down. That way you have not dropped any traffic, right? So it's more graceful taking down for maintenance. Similarly, when it's bringing up, you can do the same thing. You can bring that back up gracefully, and the traffic gets converged into this new box, or the box that is coming back into the network, and then you complete the maintenance. On the Catalyst 9300, we have something called fast software upgrade. Fast software upgrade is a feature that brings your downtime down to close to 30 seconds, right? And the way we do it is we upgrade the control plane first and then the forwarding plane. So when you have a system that is running data plane and control plane, typically what happens is when we upgrade the box, we bring the control plane and data plane down. So it's a complete shutdown of the box. What happens in FSU, which is the fast software upgrade, you bring the traffic, you go and upgrade the control plane first. So you bring the control plane down. But that means your data plane is still active, right? Your data plane only goes down when you have upgraded the control plane. That means you have saved that much time when you were doing the control plane upgrade, right? At that time, your traffic is still going on. So now when you are upgrading the forwarding plane, it takes very less amount of time, right? And that's how we are bringing the downtime close to 30 seconds. So in your normal downtime, in your normal upgrade, it might take 472 seconds. With this one, it's 50% down. And okay, so this used to be with 16.9. In the latest version, we are bringing down to 30 seconds. Okay, so that will reduce your downtime a lot. We talked about hot patching from iOS XE section, but what we have here is we have 2 types of hot patching. We have cold patching and hot patching. Cold patching is when you apply a patch, but you still need a reload. Hot patching is when you apply a patch and you don't need a reload. Hot patching is available starting 16.9. So you can actually do certain fixes that might be available on CCO with hot patches.
One question, one slide back. This is only for standalone
That's right. This is only for a standalone. This is not for a stack. That's correct. Yeah. And there are a few other limitations as well based on your topology. I can take that question offline if you have. OK, so the Catalyst 9000 has really a lot of different high availability features. Stack-wise virtual, ISSU on the Catalyst 9400, 9500, stack-wise 480 with active and standby, stack power on the 9300s. And on the Catalyst 9500, we have stack-wise virtual, ISSU with stack-wise virtual as well. OK? So that's high availability. Now, one of the important features that sits very close to the hardware is QoS. I'm going to be quick on this one. But why really we need QoS? We need QoS to have differentiated treatment for different applications that we have in our network. Voice, video, traffic are prime examples. They need certain types of treatment in the network. They cannot tolerate too much latency and jitter, for example, right? Now, how do we deal with that? We have to identify the traffic that is coming in our network and put it in different buckets. The traffic that is relevant to us, we need to know those traffic, right? The traffic that can be irrelevant, for example, there is a spam in the network. There is traffic that we don't care. We need to identify those traffic. And then there is traffic which we really don't care, that can wait for some delay, right? And that's your FTP traffic maybe, right? Now, when you have all these different kinds of traffic, the important thing that you need is you have enough in the hardware so that you can deal with those different types of traffic. In the Catalyst 9K, across all the platforms in the Catalyst 9K, we have 8 queues per port. And each queue comes along with 3 thresholds. That means you can have 24 different types of treatments for different types of traffic. Okay? And so you can really map some of these traffic to different queues based on your need or based on the RFC standards that we have. And map these to the 8 queues. Now, some of these traffic are going to the same queue. For example, CS5 and CS4 are going onto the same queue. But then you can have 2 different thresholds for the different types of traffic. So you can say CS5 should drop after CS4, right? So CS4 should not be dropped. But CS5 can be dropped at certain threshold. So you can define those thresholds, and you can define up to 3. So QoS needs different tools. And in the Catalyst 9000, we have multiple tools that we can use for QoS. How many of you have used MLS QoS in the past? OK, so some of you. MLS QoS in the Catalyst 9K, we don't have any MLS QoS. We have MQC. I'm pretty sure you'll be happy with that. So with the MQC, what we have is we have trust by default, right? And then we have the ingress tools on the ingress side. So you can classify the packet as it comes. You can police the packet and mark the packet. And then you can have other tools on the egress side. When the packet goes out, you can do some marking, policing. But the most important thing from QoS perspective is queuing. When the packet goes from ingress to egress, as soon as it hits the egress pass in the EFC that you have seen earlier, that's where we have the queues. And that's where we have the 8 queues per port. You can configure it in different ways. You can have 0 priority, 8 queues, and 3 threshold, 1 priority, 7 queue, and 3 threshold, or 2 priorities, 6 queue, and 3 thresholds, right? So you can have multiple ways of configuring that. And based on your configuration, the scheduler takes the packet and sends it out to other functions, which is policing or marking. Now you get consistent QoS across the Cat 9K family, MQC across the board, different types of models that we just talked about. We have 8 queues per port, trust by default. We also give you 2 levels of hierarchical QoS, okay? And we have WRED for congestion avoidance. And we have a buffer of 8 MB to 36 MB, right, depending on which ASIC it is. And we have talked about different ASICs. Now, different ASICs have different hardware or different buffer. And 2.0 has 8 meg total across each core. And in each of these scenarios, the bigger pie that you are seeing, that's the buffer that queues have. Other pies are basically being used by the ASIC for other functionalities. Okay? So that's a quick overview of the buffer. We also have autocause, which is basically a quick wrapper that gives you a one-line configuration instead of multiple lines of configuration for policy map. And you can use it for different applications like VoIP and others. DTS is an algorithm that basically handles the buffer in different ways. So it basically takes the buffer from other ports and gives it to a port that really needs it. This happens dynamically, and we get better burst absorption in certain cases. Okay? So this algorithm is actually running by default. What you can do is you can define different threshold on how much buffer I can take from other ports and give it to the port that really needs it. Okay, so that's DTS. If you need more information on DTS, let me know. I can talk about it after this session. So let's quickly wrap it up. So Catalyst 9K, we have talked about it from hardware perspective, from the ASIC side, platform side, as well as from the software perspective, the IOSXE, right? And we have seen multiple enhancements and fundamental changes in the Cat 9K. And that has really changed the way we are seeing our networks today, right? Catalyst 9K really makes our networks more secure than ever. We have all kinds of different security features on the Catalyst 9K, from ETA to MaxSec to trustworthy systems. I know we did not get a lot of time to talk about this session, but other sessions are talking about it, and you can get benefit from it. We have talked about a different high availability functionalities and features, all the way from StackWise Virtual, ISSU, FSU, 1+ redundancy, and so on. We have also talked about all kinds of speeds. We have talked about speeds from all the way from 10 meg all the way to 100 gig. And that's all supported on the Catalyst 9K, depending on the ports and the SKUs that you have. And that really makes your network ready for 11AX and beyond, right? We also have other features to make your network ready for IoT. And some of those features are AVB, for example, audio-video bridging. Some of these features are related to the PoE and lighting and IoT sensors that are coming on the network. We have a lot more programmability and application hosting capabilities on Cat 9K, and we have talked about some of those. And lastly, the Catalyst 9K is enabling your network for software-defined networking. Okay? This is the best box that we have ever created for software-defined access and the next-gen architecture on the campus network. So the Catalyst 9000 family is growing, and we have seen some early recognitions in multiple ways, in multiple places. It has won the CRN Product of the Year award. We have multiple external third-party reports on Catalyst 9K, and NIRCom is one of them. We also have this book that is being written by some of us, and that has a lot about the Catalyst 9K architecture. You might be able to get your hands on it if you go to the meeting village or if you talk to one of us. This is not available for sales, unfortunately. So, but we can give you one if you're really interested. It is available as an ebook on cisco.com as well. Okay? And recently, just yesterday, we have a new third-party report came out with ENTC. I'm pretty sure you are familiar with ENTC. And they are talking about the Cat 9K performance and scalability. Lastly, I would like to encourage everyone to fill up your evaluations, right? The one thing I get out of this session is the evaluation, and that's very important for me, because that's how I improve my future sessions. So next year, if you want to see something differently in this session, if you want to see more of other features or more of other platforms, please let me know and leave a note. I do read every comment that you guys leave, okay? Even if it's a 400 people room, I usually read every comment, okay? With that, I would like to thank you for sticking with me here. And thank you for coming to Cisco Live. Enjoy your rest of the day. Thanks.